Hello, everyone. We'll get started in just a minute. Well, let me welcome you all to the February ASCCT ESTIV webinar series. This is Christy Sullivan, and I'm the Secretary of the American Society for Cellular and Computational Toxicology. We partner with the European Society for Toxicology in vitro, and often other in vitro and alternative societies around the world to offer these webinars. I hope that you will consider visiting our website if you don't know about us yet, learn about the activities that we do, and consider becoming a member. You can also join our mailing lists for different fun things like job announcements and events. This webinar is recorded, and the recording will be posted on the ASCCT website a few days from now. In the webinar platform, you can ask questions for the presenters using the Q&A feature. Please use the Q&A feature and not the chat. Your questions go in there. It's a lot easier for us to keep track of them. We'll have a Q&A period after each speaker. So as soon as you think of a question for the first speaker, go ahead and put it in the Q&A, and that way we'll have questions ready once they're done. We also have enabled closed captions, and you can turn them on or off if you like in the toolbar, which is usually at the bottom of your screen. And finally, please say hello. Let us know where you're joining from and if you have as much snow as I do. So ESTIV will be having its annual Congress in summer 2026 in Maastricht. I hope you can visit the website and join their email list to stay up to date on developments and opportunities to participate. They do have session proposals open right now. And I also wanted to mention that we don't have the verbiage on the site yet, but the ASCCT meeting will be in the DC area in October 2025 this year. And we're about to open session proposals probably by the 1st of March or so, and those will be due April 25th. So again, those are session and CE proposals, and we hope you will join us to participate in the meeting. Just wanted to call your attention to a number of activities that we have on our calendar. If you go to the website, you can see this calendar and get more information and how to register. Our next webinar in this series will be March 11th, featuring 3 speakers who won awards at the last ASCCT meeting. And now I'll turn to go ahead and introduce the speakers that we have today. So first of all, we have Dr. Hung-Lin Kan, who is a postdoctoral research fellow at the National Health Research Institutes in Taiwan. His research focuses on developing alternative models to animal testing, particularly through in-silico models designed to predict toxicity endpoints. During his PhD, he created a predictive model for neurotoxicity related to Parkinson motor deficits based on the AOP concept, and currently he's working on advancing a virtual zebrafish system to assess environmental hazards and minimize the use of animals in research. The second presenter is Ricardo Tieghi, who is a Carolina research scholar at the University of North Carolina, Chapel Hill, and a computational toxicology intern at the NIEHS, part of NIH, working with Dr. Nicole Kleinstreier. His project focuses on replacing animal testing by leveraging artificial intelligence and machine learning. All right, I will turn the floor over to you, Dr. Kan, and let you share your screen.
Kirsty.
Everything looks good.
Okay, thank you. Good morning, everyone. I'm honored to be here today as a part of the ASCCT ESTIV Award winner webinar. My name is Hung-Lin Kan, and I'm a postdoc research fellow at the National Health Research Institute of Taiwan. Today, I will introduce our study about the inferring potential effects of PFAS via a novel chemical phenotype inference system, ZFinfer. With the rise of environmental pollutants, traditional animal-based risk assessment are becoming challenging. To address this, we developed a computational tool that predicts chemical-induced phenotypic effects by integrating chemical protein and gene phenotype data. This model will help us to fill the data gaps and improve toxicological predictions. So in recent years, studies have elucidated the degree of genetic conservation between humans and zebrafish. There has been growing interest in zebrafish as a model organism for drug development and toxicology research. The sequencing of zebrafish genome has revealed that approximately 70% of human genes have homologous counterparts in zebrafish, and around 82% of humans' disease-associated genes have homologs in zebrafish. The genetic similarity between zebrafish and humans suggests that zebrafish can provide valuable insights into the biological mechanisms of various human diseases. So, zebrafish assays are effective for toxicological investigation due to their small size, rapid reproduction, and conserved vertebrate biology. They show great potential as an alternative to certain animal toxicity studies and serve as a first-tier model for toxicity assessment. However, even though zebrafish assays can accelerate chemical screens, understanding the full impact of thousands of chemicals in zebrafish remains challenging. To address this, In-Silico models can assist and identify to help to prioritize chemicals that need to be evaluated by using zebrafish models and identify the potential toxicity effect targets in zebrafish. Our team has previously developed a virtual zebrafish system that provides toxicity endpoints, including the mortality, morphology, and behavioral changes. We developed a novel multitask learning method called MT4Resonate to address data scarcity and learn from various chemical spaces, demonstrating excellent performance in predicting zebrafish toxicity. Although the virtual model enhanced the efficiency of evaluations, the predictions of toxicity endpoints do not fulfill our need for comprehensive assessment of chemical exposure. So like the limitations, including the lack of the mechanism insights or sufficient linkage to the toxicity endpoint or to the disease outcomes. So to address this, we have developed a chemical disease inference system for zebrafish called ChemDisk-ZF. So what is ChemDisk-ZF? It is a comprehensive system that provides valuable information related to the chemicals of your interest. The system consists of two main components, database and analysis system. In a database, we collected and curated three types of data: chemical protein interaction data, gene phenotype disease interaction data, and gene pathway interaction data. All the interaction data was compiled and stored in databases using the MongoDB, and further be utilized for enrichment analysis. The analysis system was built using the Go programming language and including four types of toxicity endpoints: phenotypes, gene ontology, GO, pathways, and disease ontology, DO. In our system, we have already compiled information on over 400,000 chemicals and more than 20,000 zebrafish-related proteins to ensure a comprehensive and robust resource for your research and analysis. And today, we will focus on the phenotype enrichment analysis, ZFinfer. In the ZFinfer, we incorporated three different phenotype terms related to zebrafish. You can see here, the GO and the zebrafish anatomy ontology, ZFA, and also the zebrafish phenotype ontology, ZP. For model validation, we utilize chemicals from the US EPA ToxCast chemicals. we selected a total of 777 chemicals that had both toxicity records from previous studies and phenotypic prediction results from our inference system. The performance was evaluated by comparing the high-throughput toxicity data on 17 morphological endpoints in zebrafish with its predictive phenotypes. In brief, the ZFInfer system infer ontology terms affected by chemicals, followed by an additional assertion by using a keyword-based mapping method. This approach categorizes the relationships between ontologies and validation chemicals or environmental pollutants. To assess our model, we use standard performance metrics, including the sensitivity, specificity, accuracy, and predictive value. So across the 17 morphology endpoints, our system demonstrated an average sensitivity of 0.37. Data availability affects the sensitivity of our model. So particularly in the endpoints with higher interaction data, like the heart, trunk length, eyes, and brains will have a more higher sensitivity with the 0.72. Furthermore, we observed that the model's sensitivity was higher for chemicals with strong toxicity labels, indicating that the system performed well in detecting highly toxic compounds, and the sensitivity was measured at 0.49 here. We also utilized the chemical from the USEPA priority pollutant list and the EcoTox knowledge base for additional validations. The validation was tested through the rediscovery rate, which means to infer the relevant effect groups from EcoTox knowledge base, and our system achieved a high rediscovery rate of 93%. Some interesting case was observed in the validation of the US EPA priority pollutant list. So in this case, we took the chemical zinc as an example. In the EcoTox knowledge base, zinc had only limited toxicity effect data. However, in our inference system, zinc was inferred to belong to several toxicity effect groups. Due to the limited non-toxicity record in zebrafish, we expanded our search to include other fish species and found similar toxicity patterns using our system. So this trend was also observed for other chemicals such as the chloroform, naphthalene, and anthracene, suggesting that our system could be extended to various fish species and other aquatic organisms. So moreover, we apply our system to evaluate environmental pollutants, particularly the PFAS chemicals. We demonstrate two strategies to infer potential toxic effect of PFAS chemicals. So we can see here. So we have two strategies. The first strategy is to follow chemicals with the protein chemical interaction data. We can directly infer the potential toxicity endpoints. And for the chemical without chemical protein interaction data, we can infer their effect group endpoints through the molecular similarity with known chemicals. So in this case, we can find that most of the potential toxicity endpoint of PFAS was identified in behavior, development, morphological, and physiology groups. So furthermore, we use the biological data of this potential toxicity effect to construct an integrated prediction model. The web of evidence model was developed by using 4 different types of features, including the chemical structure information and the QSAR score, the virtual zebrafish models, and the gene score and phenotype score by using our ChemDCF. So we further utilize the integrated model to predict the developmental and reproductive toxicity chemicals and found that our model increased the AUC performance by nearly 4% from here. We only use the chemical structure and to have it improve in the training data set and also the independent test data set. So we're currently developing a web server with a user-friendly interface to make a ZFinfer public accessible and enhance the overall utility of the system. Through this platform, user will be able to search for specific chemicals like here. And you can search and have the human and zebrafish. So we are focused on the zebrafish today, and we will receive the inference result of the gene ontology here, the protein gene ontology, pathway, disease ontology, DO, and also the phenotypes. So furthermore, in addition for study of the potential toxicity effect of the single chemicals, we also focus on the effect caused by the chemical mixtures. So to discover more comprehensive insights of mixture risk, we first developed a chemical mixture analysis system. So future work of our about our system update will focus on the mixture effect analysis here. So in this, we also developed a user-friendly web tool that you can search mixture chemicals from here, and you can have the inference result for the chemical mixture, have the protein, geo, pathway, disease ontology, and also the phenotypes. Okay. So thanks for your attention. I would like to acknowledge the support from the NSTC Taiwan and the NHI Taiwan. And here are the members of our research team. If you are interested in our studies, or want to try our Zebrafish system, please feel free to email me. Thank you.
Great. Thanks very much, Dr. Kan. It looks like the system has a really compelling potential number of uses. I have a question to get us started. I don't see any questions yet in the Q&A, but let me ask you just a basic question that always comes to mind, which is, have you thought about how this tool could be used, or do you have are you considering outreach to regulatory agencies or companies to kind of help them use the tool?
Actually, I think maybe the ZFinfer to inference the phenotype is just the first step to fill the data gap by using the interaction data. But in the further, I think we can focus on by filtering the gene by filtered by the specific organs. Like if we have the we can collect the more different development stage in zebrafish and have the RNA sequencing data to do the gene filter and to have the more specific significant value for the to infer the specific phenotype or disease in the zebrafish, and to I think maybe just this tool focusing on to give the scientists have the prioritized way to choose what kind of the chemicals will have a certain toxicity effect groups like areas, like because most of the zebrafish data will collected in the ecotox knowledge base, but maybe some of the affected groups or the area will only have limited data, like the immunology system or the toxicant system like this one. So we can to inference this kind of the phenotypes related or the to assert like this to assertion by this kind of the gene ontology data, and to tell the scientists that maybe you can do some more immunology system tests on this kind of the toxicants. Yeah, I think maybe this is just the first step to for the users to do the prioritize. Yeah.
Okay. I also can imagine that the mixtures tool would be of a lot of interest. Could you remind me, there was a Venn diagram at the end on one of your last slides. What was that showing? I think I missed it.
This diagram, right?
Yeah.
Yeah. And this one is for because we're to infer the mixture effect by using the overall means the interaction data from these two chemicals, and also the overlap. Oh, maybe I need to, sorry. So you will have the interaction gene with this chemical and interaction gene with this chemical, and this is overlapping.
Okay.
And with we can to analyze the overall effect from these two chemicals and also the overlap it, yeah, by showing this Venn diagram. But I think maybe if the chemical mixture were over 4 chemicals, we didn't have the Venn diagram for the users. We only have the table.
Okay. All right. Yeah, that's helpful. Thank you. We have
Thank
a
you.
couple of questions now in the Q&A, so let me read those out for you. One of them is, how would you evaluate if a compound is inside the applicability domain of the model or outside?
We have to do the test. And I think we need to have. Maybe show this one. So I think maybe you are focusing on the applicability domain, but it's usually for the QSAR models. But I think maybe you can to explain by the chemical with the chemical protein interaction data and without chemical interaction data, you will have maybe directly to connect it to the applicability domain in our system. And which means that if we have the interaction data, we can directly infer. And if we didn't have the interaction data, we can do the molecular similarity. So it seems that you are a little crazy about why we can use the molecular similarity to infer the chemicals, but we have to do the test by using the same chemicals, the 777 chemicals. We do the directly inference and do the similarity inference by removing this kind of chemicals interaction data. So we can find that in our system, both the direct inference and also the based on the molecular similarity can show the similar sensitivity in the different kind of morphological toxicity group. So I think the applicability domain, this issue, well, can be solved by the molecular similarity in our system. Yeah, because usually the users will think that if we didn't have interaction data in our system, why can we can do the inference? But we use the molecular similarity and we validate it. So I think maybe we can solve the applicability domain issue. Yeah.
Okay, thank you. There's a couple more questions. Maybe we can get some quick responses to. There's a question about you, just to confirm, the model has been generated from data already available in the literature. Is that right? Yeah. And so do you plan to expand the coverage of the model in some way maybe by gathering or generating more data?
Because our, I see here, sorry. In our system, we have the two components. The first is the database. So I think we will keep going to collect more and more data because the database will update and we can have more interaction data to do a more precise inference. Yeah, because we know that the enrichment analysis will based on the more effective biodata availability. Yeah, so we will do the update about the database in further. Yeah.
Great, thank you. One last question. Are these data already used in pesticide submissions? Do you know?
I'm not sure about the pesticides because we didn't do the pesticide test. So I think we have some pesticide chemicals in the system, but I'm not sure how much and how the severity or the sensitivity about to predict this kind of the pesticide data. But if the uh, audience were curious about the research about the pesticide, maybe you can have email to me. We can have the more research about the pesticide in our system because our system were already finished, but we are do the publication revise. So after the paper will publish, we maybe we'll release our system. Yeah.
Okay,
Thank you.
thank you very much. There is one more question, but I'm going to let you go ahead and answer that by typing an answer, and we will move on to Ricardo Tieghi. Thanks again, Dr. Kan.
Thank you.
Can you see my screen?
We can. It looks like it's in outline mode still.
So it's not letting me share.
There it is. Yeah, it looks good.
Fantastic. So, good morning, everyone. My name is Ricardo Tieghi. I'm an undergraduate student at UNC Chapel Hill and an intern at the NIEHS. And I'm thrilled to share with you our project, which is called DeTox, which offers an in silico alternative to animal testing for predicting developmental toxicity, which I got a chance to present in the last ASCCT conference meeting. And so I have no conflicts of interest to declare. And I thought I'd begin my presentation by giving a very brief definition of what is developmental toxicity. So DT, or developmental toxicity, refers to the potential of chemicals to interfere with fetal development from exposure of either the parents or exposure of the developing organism before its maturity. And after chemical exposure, it can entail a series of adverse outcomes such as fetal malformations, spontaneous abortions, impaired growth of the fetus or the embryo, or even functional and cognitive deficits. And traditionally, DT is assessed with in vivo studies, for example, the OECD test guideline 414, which uses whole embryo culture assays from rats, rabbits, and other rodents, and non-rodent animals. However, DT testing using animals faces its fair share of challenges. For instance, according to the EPA, it can be quite expensive, costing upwards of $128,000 for a single chemical. It can also be quite time-consuming, and it also raises ethical concerns due to the sheer amount of animals that are used for this test. And in recent years, it has been called into question about the human relevance of these tests. For example, this report from 2022 highlights that animal testing actually shows a false negative rate of approximately 40% for 35 known human teratogens tested across 12 different species for DT. And they also show that there's only a 60 to 70% concordance across the 12 different species for over 1,400 chemicals tested for this endpoint. And so when you combine those two, we get uncertainty in the outcomes of animal testing. And when we consider that 80% of pregnant women use prescription medication during pregnancy, this creates a huge gap that puts both pregnant women and their developing offspring at risk. And so recognizing the limitations of these traditional animal models, over the past several decades, there has been this push to align with the 3 R's of toxicology, which include refining, reducing, and replacing the use of animals for toxicity testing. And these usually entail the development of NAMs, or new approach methods, which offer alternatives that tend to be more human relevant. And it has even been recognized by federal agencies such as the NIH, which has launched the Complementary Initiative for the development, validation of new approach methods. And these entail techniques such as developing new in vitro cultures, organ-on-a-chip strategies, in chemical approaches, or the focus of my talk today, in silico tools such as QSAR, which is developing machine learning models or using artificial intelligence to predict endpoints from chemical structure. And so I thought I'd provide a very brief overview of machine learning for those of you who aren't familiar. And machine learning enables us to analyze the impact of many different factors on an outcome. And so in our case here, we're using descriptors. And the descriptors we use in this project are all binary, fingerprints, and so they indicate the presence or absence of molecular fragments. And so in this case, just an example, if we have a carboxylic acid present here, it would be categorized as a 1 in our data set. And if it's absent in other molecules, it would be categorized as a 0. And then we also merge that with our biological activity, in this case, DT, into a training data, which creates a data matrix where each row represents a compound and each column represents a descriptor or your biological activity of interest. And so we can use machine learning algorithms, which we use to create models, which we validate with external performance data, and we use to extrapolate for new case studies. And so I thought I'd provide a very brief overview of the methods used in this project. So we collected data from the FDA's DailyMed, the Teratogen Information System, and independent literature data, all publicly available. And then we performed an additional literature search to verify the outcomes of all the compounds collected. And then we proceeded with data curation, which data curation involves cleaning your data through like removal of mixtures, normalizing chemotypes, and especially removal of duplicates, as having duplicates in your training and test sets of your models can drastically over or underestimate your prediction performance. And so after performing data curation, we calculate descriptors, perform the machine learning models, and deploy the web platform called DeTox. And so for this project, we applied binary classifications for all our compounds, where they were either labeled as developmentally toxic versus non-toxic. And so adverse outcomes that we considered for compounds to be toxic included things such as mentioned previously, fetal malformations, structural abnormalities, the potential of a chemical or drug to cause spontaneous abortions when taken during a specific trimester, cognitive deficits, altered growth, or even functional and behavioral changes observed at any point during fetal developments. And so here's just an example of extraction from FDA drug data from DailyMed. We extracted 47 different thousand records approximately. And up until recent years, the FDA used this classification scheme where they assigned categories for how safe drugs were to be used during pregnancy. And categories A and B represents no risk in human or animal studies. Category C are inconclusive data, and categories D and X represents risk. And so we removed compounds with inconclusive studies and analyzed the outcomes with non-toxic and toxic outcomes. We also collected compounds from independent literature sources, which yielded an additional 450 records for investigation. And I like to have this slide to highlight the importance of data curation. You can see, for instance, from the FDA, what originally appears to be a rich series of data points, after removing inconsistent data, mixtures, and duplicates, you can see we end with only 221 compounds, losing almost 98% of the data we originally started with for this endpoint. And so it's a common theme across the 4 different data sets we collected. When we perform data curation, we eventually lose a few compounds. And so after we performed the data curation, we also performed an external literature search. We wanted to find at least an additional source that could confirm the toxicity or non-toxicity of each compound in our data sets. And so we went to Google Scholar and PubMed with these key search terms and identified trimester-specific studies in either animals or humans, which identified our outcome of interest. And we only included studies that were done under the OECD or EPA guidelines, done in rats, rabbits, or mice, or specifically human studies done with greater than 50 individuals. And so if any outcome that was, or any compound was previously labeled as non-toxic, but recent epidemiological data showed that it was actually toxic in humans, we updated that classification prior to running our models. And so just as a quick summary, we developed 4 different independent data sets where a compound was labeled as its overall developmental toxicity if it identified risk in any of the trimesters. And we also built trimester-specific data sets based on compounds that strictly had classifications tested during those trimesters. And so this resulted in approximately 384 different compounds. As you can see here, their distributions ranged from close to 60 compounds with imbalanced data sets to close to 200-ish compounds for the overall toxicity data set. And from the literature search, 54% of these compounds actually had at least one human epidemiological study with greater than 50 humans, highlighting their classification as either toxic or non-toxic, and the remainder were only animal assays were available. And so we also took these 384 compounds and we ran a preliminary chemical space analysis. This enables us to identify class-specific groups and to understand the distribution of our data set and also the features of the compounds that are present. And for instance, we can identify some interesting clusters. For instance, all these beta-lactam antibiotics, such as cephalosporins or penicillins here, all tended to cluster together, forming non-toxic clusters. And then we also found, perhaps more interestingly, compounds which had toxic clusters, such as anticoagulants, or as we imagined, agrochemicals clustered together. And so did these aminoglycoside antibiotics. And so the interesting thing about chemical space analysis, it also enables us to identify activity cliffs, which is essentially when you have two chemicals which have a very similar chemical structure, but drastically different toxicity outcomes, as you can see represented here by the circles. And so just as a single example, we have this compound here, which is non-toxic. And in our data set, it was actually sourced from a human epidemiological study with greater than 6,000 births. And the other endpoint, as you can see, has a very similar chemical scaffold, differing only at a few atoms. However, it was sourced in rats. So it serves as a cautionary note when extrapolating results from our model, and perhaps suggests that DeTox should be used as an integrated strategy, combining various different new approach methods to predict developmental toxicity. And so overall, we built 24 different binary classification models using binary fingerprints, and the machine learning algorithms we explored included random forests, LightGBM, and support vector machines. And here you can see a preliminary performance assessment of our models. So here I'm comparing the 4 best performing models that we had for each data sets and Y randomized models. And you can see our models were performing significantly better than the randomized models. And I use 60% for animal assays just as a base comparison based on the reported predictive positive accuracy. And so you can see in general, our models perform similarly or better than existing animal assays and better than random models. And so here I have a more broken down trimester specific model performance. It's a lot of dots, so I'll just walk you quickly through it. Basically, our models had accuracies ranging from 60 to 80%, and similarly for sensitivity and specificity. That's how we're predicting the positive and negative classes. Those tended to range for sensitivity, for instance, from 80s close to 90s, and AUC, which is a common metric for area under the curve, also ranged from 80s to 90s, depending on the data sets. And so we had built these models, but we wanted to make them publicly accessible. So we deployed them into a web platform, which is freely available at this link. And then in the platform, you can simply sketch your compound or input your SMILES and get predictions with fragment contribution analysis. So if you access this link or this QR code, you should be hopefully greeted by this landing page where you can insert your SMILES for your compound here, or draw it in the box, select the model options which you wish to use, click the Get Properties button, and you should receive the report which has your molecule and the prediction, is it inside or outside the applicability domain, and a fragment contribution analysis map, which states which atoms are being responsible for toxicity versus non-toxicity. And so next, we just wanted to perform an external validation performance of our models. How does it compare to existing published models in the space? And so the Caesar model group developed developmental toxicity models in 2009. And as you can see, there's our in purple here. Our models perform generally similar or slightly better in some cases than existing models for developmental toxicity, with the benefit that our models also offer trimester-specific predictions, whereas the Caesar only offers a single model. And so we also took all the compounds from the Caesar project that were outside of our training sets, and we performed an external validation, and we predicted all of those. And so as you can see here, it tells it's a lot of dots on the screen. So it tells a story where our accuracies ranged from 60% to close to 80%, depending on the data sets. And I think the most interesting to highlight is the the lackluster performance in terms of the NPV and the sensitivity, this highlights our model isn't predicting the negative classes as correctly. And I think one of the reasons for that would possibly be the imbalance in the data sets, but also the lack of true negatives in the data set could be an issue. And so just to wrap up, we also performed a virtual screening of the DNT library data. This is the NIEHS National Toxicology Program owned initiative, which contain compounds that are 87 confirmed neurodevelopmental toxicants. And so we took all the compounds that were in our training sets, removed those, and predicted compounds inside our applicability domain. And we found that our model was able to correctly classify these 15 as non-toxic. And they included chemicals such as drugs, flame retardants, different industrial use chemicals, or polyaromatic hydrocarbons. And so just in conclusion here, I have shown you that in-silico approaches offer a fast and cost-effective alternative to animal testing. And we built a publicly available database of compounds labeled by their developmental toxicity potential. And then we use this data sets to build machine learning models, which we deployed as a web platform, which is freely available. And so I actually have a very quick discussion of some future directions, which came up during my ASCCT talk. And so one of the limitations of our models is that it doesn't offer a mechanistic interpretation of the compounds. So with that in mind, in support of this initial guidance published by the OECD in November 2023, supporting an in vitro testing battery of developmental neurotoxicity, the OECD identified 17 different in vitro assays that cover key developmental neurotoxicity processes ranging from proliferation to migration or synaptogenesis. And so with that in mind, we are planning to use knowledge graphs, which are a way of integrating a series of different databases and harmonizing them into what they call semantic triplets, where, for instance, if we have a specific chemical, and we know that chemical targets has a specific target or binds to a target, and that target leads to a disease, then this enables us to identify inferred relationships where a drug can cause a disease. And so we're planning to use this infrastructure and these semantic triplets using toxicological data to identify key novel events and molecular initiating mechanisms for developmental neurotoxicity. And then, so these are some of the data sources we are planning to incorporate, and they include the DNT diver data and the EPA's CompTox chemicals dashboard. When combined into the DNT knowledge graph using Neo4j, can actually yield a data set which has over 1.3 million nodes for over 8,000 compounds, which will hopefully enable us to identify novel adverse outcome pathways for DNT, which will support the development of new in vitro assays and NAMs for developmental toxicity. And so with that, I'd like to thank all these amazing people from the UNC Molecular Modeling Lab, but also the NIEHS NICEDM group and ASCCT for the opportunity. Thank you for your time.
Great. Thank you, Ricardo. That was a great presentation. We've got some questions already coming in. But I have a really basic question that I'm sorry, maybe I just missed this, but in the structure graphs where you, or the little pictures where you were showing the different structures and they had sort of red highlighting and blue highlighting, what is the significance to the different colors?
Let me see. Are you talking about this one?
No, when you have the pictures of all of the different
Let's see.
structures.
This one, right? Like these ones. Yeah, so the green here represents toxicity and the red represents non-toxic. So these compounds are known for contributing to non-toxicity of the molecules, and these compounds are contributing to toxicity.
Okay, great. Thank you.
Yeah, this is more for a drug design sort of species. If you were a medicinal chemist and you're interested in manipulating the the molecule to maximize your activity data. Yeah.
Okay, cool. Thanks. All right. So one question we have is do you think that many of the activity cliffs can be explained with species differences rather than the phys-chem properties, considering the example you gave?
Yeah, I think it's a great question. I think it's actually a mixture of both. I do think species differences explains a good amount of those, but not all. And I do think the difference in phys chemicals parameters, like and just the pharmacokinetic properties and distribution of data compared to animals, but also anatomical differences between each of the species. I think all of those are contributing factors. It's a very complex endpoint. Yeah.
Yeah, yeah. Um, Another question is uh, sort of maybe a general question about models. They're wondering if, or maybe your particular model is helpful to predict for the compounds which we don't have any scientific data yet. Maybe you can.
Yeah, I think it's definitely an option, right? Instead of running a test for which costs thousands of dollars and months of time, you can run a preliminary query. It's free and it offers an initial insight into the potential risks. So I think the vision for this project is to incorporate it with other NAMs, such as in vitro and chemical. And in the future, you run a preliminary screening with the in-silico models combined with these other tools. And then, if necessary, then you identify other animal tests to run, or
Yeah,
even just skip the animal tests and test in humans.
right. Okay. Have you compared fragment toxicity information you develop with two-dimensional molecular determinants described extensively by the USEPA toxicity estimation software tool?
No, I
Maybe you
haven't.
can look at the question and read it. That was a complicated one.
Yeah, I think I'd have to spend some time with that. I don't think I have. No, we haven't done that, but now it's on the radar, so I'll definitely do it in the future.
Great, great. Thanks, Celine.
Mhm.
And could you explain a little bit how you derived the, I guess, the developmental tox classifications from the literature? Did you manually review papers or did you extract digitally?
Yeah, so they were all manually investigated. So just manual curation, reading hundreds of abstracts and
Yeah.
analyzing for outcome. Yeah, so it's essentially it was derived from we try to be as comprehensive as possible, including any of the adverse outcomes. We try to only include studies that had followed the OECD guidelines. So that was the general approach to classification, but it was all done manually. I think perhaps nowadays it could be automated with the right
Yeah.
language models. However, we started this project before before that was popular.
Yep. It would be interesting to compare the manual and the language model results.
Yeah.
So another question is, does your output for the model that you said was available provide the closest analogs from the training set in the prediction outcome?
Oh, unfortunately it doesn't, but I do think that's a feature we can incorporate. So I'll definitely do it. I'll definitely investigate that.
Great. I think we have, okay, so this is in the chat, not in the Q&A, but we're wondering if you have a suggestion when you find two compounds with a similar structure, but one is clear evidence for human toxicity, other not.
Yeah, so the approach we took here, for instance, is let's say we had historical data from the FDA Daily Med, which had
Yeah,
a compound as non-toxic, but then a recent epidemiological study with thousands of pregnant women identified that it was actually developmentally toxic. Here, we chose to classify the compound as toxic, even though the historical animal data went against that. But I think in the end scheme of things, we want to make these NAMs as human relevant as possible.
yeah.
I think incorporating pharmacovigilance data or just human-derived data as much as possible will ultimately push forward the field and NAMs in this space. Mhm.
Great, thank you. Well, we have time. We have one more question so far. So this is, I think they're wondering about applying your model for something new to identify or predict idiosyncratic adverse reactions for sensitive subpopulations. Have you thought about that?
That's not something we had considered previously, but it does sound like an interesting approach to consider as a future direction or as a case study, an example of the model in practice.
Yeah. Another question came in. It's a little outside your expertise. If you're planning to apply this approach to drug-induced liver injury, I know there are a lot of DILI, different in silico and in vitro models for DILI, but I'll let you respond.
Yeah, I'm not too familiar with drug induced. I do think it's always important to consider when building models to consider endpoint specific data sets. So here I can't recall of any papers that I read that actually talked about liver and linking developmental toxicity for this project. And so I'd be a little hesitant to use it directly to predict drug-induced liver toxicity. And I'd rely more on the models that were built specifically for the endpoints. However, you could always run the predictions, right? And see how those compare.
Yep.
Mhm.
Well, we're done with all the questions. Both of you got a good number of questions, so that's what we'd like to see. I will thank both Ricardo and Hung-Lin for coming to give your presentations. Thanks to all of you for listening and for your questions and engaging. And again, we'll post the recording on the ASCCT website in a little while. And hope you all have a nice Friday and weekend. All right, thanks very much. Bye-bye, everyone.